Hey guys, welcome back. Day 40. We got enthalpy today. All right, so recall that work, right? Work, this was W. Work requires coherent or concerted, organized motion of the particles of a system, right? Wind blowing is a great example. The air pushing the piston in the cylinder in one direction is a good example. So organized motion, that's very important. Now, when we do work on a system, if the system doesn't expand, no work is done. All right? And we're going to call that constant volume. All right? Okay, so there's no change. So when we talk about what work is negative P dV, right? Well, if dV equals 0, no change in volume, so 0 times the P, doesn't matter what the pressure is, and it's negative, it's still going to be 0. So work is 0. So therefore, any change in the internal energy, U here, right, any change in that, let's highlight it. Any change in U is only to the heat. That's heat. So delta U equals Q, or delta U equals QV. That V instigating, constant volume. All right. So that's what happens. Now, like how we do our lives, we are always doing most things open to air pressure. Now, the air pressure does change, but in a 2-3 hour window, it can change a lot, but a lot of times it's pretty constant in that 2 to 3 hour window. All right. Okay. So then there's work done, right? Because we're in constant pressure. All right. But so W equals negative P dV because an increase in volume means the system is doing work on the surroundings, and the internal energy of the system decreases. So our internal energy here, heat, work, substitute in negative P dV for W, so internal energy, heat minus the work. All right, and so now we're going to rearrange and bring this to this side, but we're going to flip it around. So QP, so that means constant pressure, heat transfer, internal energy, and work. Now, how do we measure heat transfer? Well, that's pretty easy. We measure it, and that's a thermometer, right? Temperature change, that's easy to measure. But if you think about a reaction in, let's say, a container, a beaker, and it produces heat, or it even absorbs heat, well, the volume of the water is going to change. Very difficult to measure how much it changed, right? And so we can't really, encompass that. So we define a new function called enthalpy, H. So the change in enthalpy, all right, the change in enthalpy is going to equal the heat transfer at constant pressure, right, which incorporates the work done. Okay? Now, this works for us. This is a very good approximation, right? So the difference between delta U and delta H is small for reactions that do not involve a change in gas volume, all right? So when we're talking about liquids and solids and that type of thing, delta U and delta H pretty good. Now, if you're doing gas expansion, the change in volume is big, and so it's going to change, all right? So enthalpy means heat inside or heat content. And so, as you can see, delta H is the heat gained or lost by a system at constant pressure. All right, so if we look at this, look at these graphs. H is your heat content. Think of it kind of as your chemical potential energy. But your heat content, your enthalpy, how much it has. And then the x-axis is the reaction. So you can think of it as time, but it's not necessarily as time. It's just a snapshot of if the reaction proceeded. Right? And so if the energy of the reactants, is bigger than the products, right? That would be a negative delta H. And so hydrogen plus oxygen going to water, that much heat released, so delta H is negative. Endothermic is the opposite. Your reactants are here, your products are there. You need energy to go up, right? We need energy to go up. So we got 90 kilojoules of heat is added to these two reactants to make your product. And so delta H is positive. All right? And so that's an endothermic reaction. So those are the two, that's the differences. And so what we're talking about here, the takeaway is that delta H is heat transfer, heat gain or loss by a system at constant pressure, right? And we're going to use that heat gain or loss to predict, if reaction, what we can do with it. All right, moving on. How we calculate enthalpy. There's three ways. First is Hess's law. All right, and so it doesn't matter how you get there because enthalpy is a state function. What does that mean? It means, if we go back up to this, right, the state of the reactants and the state of the products. It does not matter the path, how to get there. I can go over here, you can come down, like that. It doesn't matter, right? The path doesn't matter. Flying for humans is a nice analogy. You care that you land, what airport are you taking off from, at what time, and what airport are you going to, at what time. It depends on your financial situation and the time you have. Maybe you'll take a stop. Maybe you do 2 stops and save a couple $100. Maybe you will just want to do nonstop and pay the extra, right? Sometimes you have to stop, right? A lot of times you go international. Sometimes you have to stop, right? And that's just how it works, okay? And so we want you to know that it doesn't matter the route taken, it just matters the initial state and the final state for Hess's law. And with that, we can use different reactions that are known to figure out unknown, right? And so think of Hess's law as kind of like elimination in algebra, right? Here's what I like to do, all right? I got my reactants and my products. So reactants, CO, 1/2 O2. Products, CO2. Oh, didn't change color. Okay. What I like to do, so I'm given these, right? And so what I do is CO2 is here. And then I got CO on this side and 1/2 O2 on that side. Now, with elimination, just like in algebra, right? If I flip the first reaction, like it says I'm going to reverse equation 1. If I flip the first reaction, what happens to delta H, you think? All right? If I flip the reaction, the delta H changes. Is that right? Flip reaction. Flip sign. Now, what if I needed to multiply everything by 2? Right? Make coefficients. So what if I'm not doing this, but what if I had to put a 2 here, a 2 there, a 2 there, and a 1 there? Well, then I'd have doubled delta H, the same thing. All right? If I needed to do a 3 and a 3 and a 3 and 1.5, then I'd be times 3, right? That's how that works. If I divide by 2, if I needed to half equation 2, let's say I needed to half it, then I'd get half of delta H. I don't need to half it. I just need to flip equation 1. So if I reverse equation 1, I get CO gas plus 1/2 O2 gas, giving me carbon solid and O2 gas, with a delta H now of positive 110 kilojoules. If I keep equation 2 as it is, C solid plus O2 gas going to CO2 gas. I'll get my highlighter back out. All right? And that's what we have. Oh, I forgot delta H. Delta H here is negative 394 kilojoules. So if I were to add these up, all right, what do you notice? What cancels? You guys see how O2 and O2 cancel? And that's carbon and carbon cancel. If I add them up, if I add these two reactions, so I'd have CO gas plus 1/2 O2 gas going to CO2. And delta H then for the new reaction would be negative 284. All right, so that's all I basically did is eliminate what's not needed, kind of like if I wanted to eliminate something in algebra and go down. All right, so let's try one. I want you to try it, okay? So pause me, try it, and come back. All right, I hope you paused and came back. So we're calculating graphite, hydrogen gas, going to C2H6, which is ethane. So I look for my C2H6, it's there. All right, and I look for my other reactants, H2 and 2C, there's graphite, and H2 is there. All right, so what do we need to do? All right, if I look at this. Well, graphite's on the correct side, except if you notice, and then I got a 2 there, a 3 there, and I have a 2 there. So it looks like I need to double the first reaction, which means we double delta H. The second one, it looks like I need to triple. And the third one looks like I need to flip and half. All right, let's try it. I got 2 carbon graphite plus 2 O2 gas going to 2 CO2 gas. And now that delta H is what? Negative 393.5 times 2. I think it's negative 787.0 kilojoules per mole. And then I would have 3 H2 gas plus 3/2 O2 gas, right, going to 3 H2O liquid. Delta H is negative 285.8 times 3, negative 857.4 kilojoules per mole. And then we would have 2 CO2, because I'm flipping, plus 3 H2O going to C2H6 gas plus 1/2. All right, 1/2, 7/2 O2 gas. And that delta H is going to be, 1/2 of 3120.8. So 1560.4, positive 1560.4 kilojoules per mole. All right. My highlighter back out. I have graphite and H2. And then we have this product. Okay. Let's do some canceling. I got CO2. No, I don't want to highlight it. I want to X it out. CO2 gone. 2 CO2 gone. All right. Water. I can do 3 H2O gone and 3 H2O gone. All right. 2O2 is the same thing as 4 halves. 4 and 3 is 7 halves. 7 halves. Excellent. All the oxygen is gone. That works out beautifully. So I'm left with my 2 carbon, which is graphite, plus 3H2, which is a gas, going to C2H6, which is a gas. And delta H, I got 1560.4 positive, minus 787, minus 857.4. Looks like I got negative 84 kilojoules per mole. Hopefully that's what you got. Hopefully I'm correct. And yeah. So that is Hess's law. That's the first way we calculate delta H. Second way, standard enthalpies of formation. Delta H F, right? Okay, now, this degree sign means standard state, which is usually 1 atmosphere, 25 degrees Celsius, all right? And the F is formation. The standard molar enthalpy, or standard molar heat of formation, right, is how much basically energy as heat is released or absorbed when 1 mole of substance in its standard state is made from its constituent elements, the elements that make it up, in their standard states. Now, the standard states of the elements might not be so clear to you unless you have a certain periodic table. Like in the classrooms we teach at, we have Fisher scientific periodic tables that show you the state, right? So we have red ones that are all gases. There's 2 blue ones, which are liquids, and all the black ones are solids. Now, some elements don't exist in nature, like number 43, technetium, and it's hollowed out, so it tells you that. I don't know. I think you guys know that hydrogen is a gas. The noble gases are all gases. And then nitrogen's a gas, which is the main component, air. Oxygen's a gas, right? And then fluorine and chlorine are gas. And that's all the gases. So it's just H, NOFCl, and then the noble gases. Those are the only gases. All right? The liquids, well, mercury is one of them, liquid mercury. Bromine is the other liquid. So you got bromine and mercury are 2 liquids, right? And we covered this in the periodic table day 1. All right? And then the solids are the rest of them. All the rest of them are solids. All right? So now, by definition, an element in its standard state must have a delta HF equal to 0. All right? That means the standard enthalpy of formation of O2 is 0. Okay? That's just how it was created. It's how it came. So calculations. Delta H of a reaction is equal to sigma, which is the sum, delta H of formation of the products minus the sum, delta H F standard of the reactants. All right. Products minus reactants. Okay? So let's do an example. How much energy is released when methane burns? Now you see right away, we don't give you O2 here, right? We didn't forget, right? O2 is 0. So now delta H of the reaction is the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants. So delta H, products, CO2 and H2O. Now, there are 2 H2Os, and that matters, right? There's 2 moles of water, and that matters. Reactants, we have CH4, and we have O2. And there are 2 moles of O2. So now we're going to put numbers in. Delta H, CO2, negative 394 kilojoules, plus 2 times negative 286. CH4, negative 75, plus 2 times 0. All right, now, however you do this, it doesn't really matter to me. If you do the math individually, do it all out. Just the secret that people run into is this negative and that negative. Okay, so if you need to break it down more, right, I typically don't. But if you need to do the purple, so you would do negative 394 plus 2 times negative 286, and I get negative 966 kilojoules minus, and then I have negative 75 kilojoules. So overall, delta H of the reaction is equal to negative 891 kilojoules per 1 mole of methane. Right? And that, by the way, is a heat of combustion. When 1 mole of something burns, how much energy does it release? So that is delta H, all right, of formation. One more. We can approximate delta H with bonds breaking and bonds making, because when a bond is broken, right, energy is released. When a bond is formed, energy is required. So a bond is formed, when a bond is formed, right, energy is released. When a bond is broken, energy is required. All right. So if I break a bond, no matter if the bond wants to break, it still takes energy to do it. And when bonds are formed, always energy is released. Sometimes it's a tiny bit, sometimes it's a lot bit. All right. But that's the way it is. All right. So now the energy of the reaction is equal to the energy of bonds broken minus the energy of bonds formed. All right, so when we got the bonds involved, that might have sparked the Lewis. Lewis structures would be what we're going to be doing here. So our example, calculate the heat of formation of hydrazine, which is N2H4. Well, because if you look, delta HF, we know that delta HF standard of N2 is 0 and H2 is 0, so we want to know. So that means we don't know what the delta HF standard is. And we know that, if we did the whole, like we did up here, the delta H of the reaction would be the delta H of formation of N2H4 minus 0, because those are that, right? So we're not doing that. We don't have the energy, we don't have the information to do that. We have the bond energies. So first of all, delta H of the reaction is equal to energy of bonds broken minus the energy of bonds formed. And we'll do this. Okay. So now, if we look at this, I have N2. Well, we got to go back to our valence electrons. N2, I think N has 5 valence electrons, so that's 10 electrons for N2. 2 there. And so we have 10 and 14 electrons there. All right, so if you forgot how to do that, we need to go back to previous lectures and look into that, right? Because we'll definitely need to know that. So N2, drawing it. I got 2 N's. All right, bond them 2, 4, 6, 8, 10. Well, that's not going to work. Double bond 1. Oh, still not working. Double bond. Triple bond. There's N2. H2. H and H. And then N2H4. Well, what do we think happens? Probably 2 N's. Each N gets 2 H's. I'm going to try that. H, H, N, N, H, H. 2, 4, 6, 8, 10, 12, 14. Does that work? I think so. Although I don't like this one. That's better. Formal charges. Hydrogen's good. 1, 2, 3, 4, 5. Has 5. Brought in 5. Good. 1, 2, 3, 4, 5. Good. We're good. So I like it. All right. And again, if we need to go back and look, go back and look. Especially if you have to take Chem 2, organic chemistry. This is a big skill, especially in organic chemistry. Delta H of the reaction is equal to bonds broken. We have the N triple bond N, and we have the H single bond H. And we have 2 of those. Minus bonds formed. I have N single bond N and N single bond H. And it looks like I have 4 N single bond H's. Don't we? All right, there's 4 of them. Okay, now let's put in some numbers. Now, if you look, instead of just breaking 2 bonds, I'm saying we break the whole bond and make a whole new bond. Hopefully that made sense. Not just, well, you only broke 2/3 of it. Just break that bond and make the new bond. All right now. So delta H of the reaction is equal to triple bond, which is 945 kilojoules per mole. And HH is 436 kilojoules per mole. And there are 2 of them. Minus NN, which is 227 kilojoules per mole. And NH is that's horrible. Try it again, 391 kilojoules per mole. All right. So now, if I were you, depending on how you are with your calculator and how confident you are, the bond's broken, I would do the blue first, then the bond's formed. Now, I don't do that. I usually just do it all at once, but that's up to you and how good you are at your calculator and how consistent you get the correct number. So 945 plus 2 times 436. I got 1817 in blue. Minus in pink, I get 227 plus 4 times 391. I get 1791 kilojoules per mole. So if we do delta H of the reaction, which is the same thing as delta H F of N2H4, we should get 1817 minus 1791. Oh, I think I made a mistake. Did I make a mistake in there? I had to make a mistake. Let's look. So 945 17, 227. No, that's getting 26. What? Oh, I'm getting 26 kilojoules per mole. Hopefully that's what you got. Let me know if you didn't. Send me an email. All right. So that would be it. Because next we're going to calorimetry. So that's it. Hopefully that makes sense. Yeah. That should be the right answer. All right. If you have any questions, reach out to me. Otherwise, we'll see you next time. Take care, guys. Goodbye.